to be sure you remember what a wave is. Oh my gosh, I forgot my chalk. What is a wave? A wave, remember, is when a disturbance moves through a medium. Oh, sorry, IUM. Remember, so like the one we really did was the string wave. If I make a little pulse here and watch it go, this is a little too fast, but it goes back and forth real fast, right? That pulse, if I had it looser, you'd be able to see that pulse move this way and bounce back this way, back and forth, right? That's what a wave is. And we would describe it mathematically. Usually we'd have like space here, position here. We'd have the disturbance here for a string. That's like the y position of the disturbance. And we'd draw it. And we usually did sinusoidal waves. And we'd say, well, it's moving at some wave speed v like that, right? Because it's a function of position and time. It's a dynamic thing. So we plot it versus position, give it some v. And we talked about various kinds. We talked about string waves. We talked about sound waves. This time, we're going to talk a little bit about water surface waves. We're not really going to do it theoretically, but you'll have homework problems about it. And you'll have to understand that you don't need to know the physics of the water surface. You just need to know the frequency and the wavelength, and it's just like any other wave. And then, of course, we're going to do light waves this semester. Okay? So last semester, 125, we did traveling waves. Okay, do you want the British spellings or do you want the... I've got to go with it, right? The traveling waves, something growing up in Red Oak, Texas made me British speller. I don't know how it happened. Probably my teacher didn't know how to spell, so that's a likely thing. Traveling waves, and we described them mathematically. A traveling wave means like a sinusoid moving down the thing, or a pulse moving down the thing. So we said, okay, the y, so for a string, y is the deflection up and down. It equals, and this is the formula, a sine kx minus omega t plus phi. That was the mathematical way we described the wave, the traveling wave. So it is important that you know what all those letters are, okay? Especially if you didn't take 125. All right, so y, this is the disturbance. For a string, it's the y position. For air, it's the pressure. For sound, it's the air pressure. These are independent variables. I hope you know what that means, right? These are the ones like the x and the function of time. These are the ones that vary. There they are again, right? The independent variables. It's a function of two variables. That's what makes it complicated. A, maybe you can imagine, is the amplitude. Since we do most of our theory in terms of sine waves, we have amplitudes, right? That was not so bad. And then K, oh my God, what was K? K is the spatial frequency. Ugh. And it's just a fancy physics way of talking about the wavelength. K is just 2 pi over the wavelength. Its real name is the wave number because it's the number of waves per meter. It's related to the number of waves per meter. Omega. That you kind of know from vibrations. That's the angular frequency. But it's just related to the good old Hertz frequency that you know by a 2 pi. Right, so K and omega are really just restating lambda and F frequency in radians, in 2 pi, using a 2 pi. And then the dreaded phase constant. You thought it was dreaded last semester. Oh my God. I'm sorry, I shouldn't have that attitude. You're going to love the phase constant. Okay? All right. That's what we did with traveling waves. Right? A lot of homework problems related to that. You'd want to be able to understand how that behaves. If this is all Greek to you, and you're not Greek, then you should look at chapter 16. Right? Remind yourself, chapter 16, what we talked about, what all that means. So that's traveling waves. But what we're doing in this current chapter is a standing wave. So this is a different kind of wave. Let's see. Standing wave. A standing wave is basically an oscillating sinusoid. Sinusoid, and that's what I drew there, an oscillating sinusoid. That doesn't propagate. Right, a sinusoid that doesn't go anywhere. right? How would we make that happen? Let's look at a few first here. So here is my clamped string, and let's see how we can make it move. The way you make it move is instead of hitting it with a pulse, here's my phone number. If you weren't here last semester, you'll figure it out. Okay. I'm just really friendly. Okay. Just call me. So the way you can excite a standing wave is instead of pulsing it, you can vibrate it here. So this is this thing that's going to shake the wave here once I get it on there right. Oh dear, let's see. No, that's the wrong one. Here we go. And I got to plug it in. People were tripping over it. Rogue bands of students, not even this class, wandering through here. Just trying to get on my nerves. Let's see. There we go. Okay, here we go. That was my impression of a standing wave. So what we're going to do is start shaking it and see that basically nothing interesting happens. Hey, it's like physics. But let's see. Nothing, 12 hertz. It's just jiggling around, you know. Oh, wait, what was that? This is like how we used to listen to the radio. Wait, no, okay. You have no idea what I'm talking about. There we go. Can anybody see that at all? All right, you can see it a little bit. Yeah. What you're supposed to be seeing here is you get a big amplitude here, constant big amplitude, and then nothing here. Right? Then it just stops here. Let me give you some sweater contrast here. Nothing here, big amplitude here, right? Nothing here. Look at that. And then a big amplitude here, constant, and then nothing here. Right? Big amplitude. So it's a constant pattern. But it doesn't always happen, right? It only happens at certain frequencies. So this is at 18.2 hertz. So what if I just say, well, what about 17.2 hertz? Or 16.2 hertz? Nothing. It's kind of it's shaking around. But what if I keep going down to maybe, 14.2. Let me tune it up a little bit. Nice. Look at that. 14.7, something like that. 14.5 hertz. And suddenly at certain frequencies we get this magical motion here where we have a big amplitude and then nothing and then a big amplitude. So those are standing waves, right? So maybe you've seen those in some inferior physics class that you took before you came here. So let's draw them. Just kidding. It's just a joke. Everything is just a joke, people. You got to calm down. Okay, so shit. Let's see. I missed. There we go. So it looks kind of like this at one point, but then later it kind of looks like this, right? So you just see this. It's like a blur. It's so fast. It just looks like that. But what's really happening is actually more, I'll just draw it on top. Well, what's really happening, I'll draw it below. In reality is it's doing this. You got one coming like that at one time, and then later it's doing this. It's really a sinusoid that's just going up and down like that. Right? So this is now, and this is later. A half cycle later. Right? Up, down, up, down, up, down, up, down. These were first noticed by the greatest scientist who ever lived. Does anybody know who the greatest scientist that ever lived was? You would think it's subjective, but it is not. It is objective. The greatest scientist that ever lived was Michael Faraday. These were discovered by Michael Faraday. Anybody who doesn't think that he was the greatest scientist that ever lived, just there's the door. Okay, we don't even need to talk. Okay, you just instantly leave. Okay, so now we got to think about this. And now, do you believe me that it's really going like that, or do we want to do the fun demo? Let's see. So it's really going like that. Oh God, what time is it? Oh, we're so screwed. Okay, it's really going like that. So we're going to get dark here. It's about to get serious here. And now, can you see it? No. What we're going to do is, if you put a strobe light on it, what you can do is strobe it at a frequency slightly different from how it's vibrating. And then you see it at different points in its cycle. Right? Okay, so this we have to hide this from the undergrads or it'll be way too much fun. Oh, wow, look at that. Barely moving up and down. See? So there you can see it's actually going up and down like a sine wave. Up, down. And you can see the node really isn't moving. Look at the node. And then here's the antinode. And sometimes I can actually stop it. Oh, that's too fast. Can it stop? Can we stop time? It seems like my lecture stopped time, I know, but now I'm going to actually stop time. And time is Stop. Just call me Thanos. There we go. Look at that. Look at that. Time has stopped. Oh, my God. So it really is moving up and down like that, you see? So that's just showing you now, if you drink a lot of coffee like I do, you don't need that to see it moving up and down. I can actually track it up to 50 hertz. I can say, oh, yeah, it's a sine wave. Yeah, very clearly. So now the question is, how do we describe this mathematically? That's the real question. So we know we have this new kind of weird motion, kind of exciting, but this doesn't describe it. This describes a pulse moving down. So the way we describe this one, all the same parameters and variables. It has an amplitude, clearly. It's related to a sine wave. And all you do is you separate the space and time. Right? So this is the equation for a sine wave, or for a standing wave. Okay? So you can see it's different. Here, if you put kx minus omega t in a function, that predicts, or that describes a function translating down the medium. If you separate kx and omega t, that describes a stationary sinusoidal shape, kx, that's oscillating in time, omega t. Right? That's all it is. So one skill is to be able to understand what that means. Okay? We don't use that equation too much because there's not much to do with it. But an example is I could say, hey, the standing mode is described by 4 equals sine 3x plus cosine 2t. And ask you, what's the wave number? 4. Right? So you need to know where those are. And the only other thing maybe I would say from last semester to know also is how to get the velocity. Omega equals vk. Right? So if you saw an expression like this with a number here and a number here, you could get the speed, the wave speed, because v, it's just omega over k. So that's one thing you need to be able to do. So that's the limit of needing to be able to interpret these expressions. What we really do is use them a different way that I'm about to show you. Okay. Do we stop at 10? Is that what we do? 25 to 10? Yeah, okay, good. I forgot. Okay. Now let's see how we're going to use this real quick. Or what are we going to do with this solution which we have been presented here? Let's see. Oh, I forgot. I had a few bullets about this. Here we go. Oh, not bullets. I don't want to call them bullets. I think it's too violent. I have a few, I think, happy facts. That's what it was. So nodes, we got to define a few things. Nodes are where the string doesn't move. Okay, so those things I pointed to where it's stationary, there's a node, right? Node right there. And then antinodes are where you have maximum amplitude. Where max amplitude, the maximum motion, and we pointed to a bunch of those as well, right? Nodes, antinodes. And then the main thing that we sort of showed when we were tuning it is that standing waves only occur at certain frequencies. Only at certain frequencies. Sorry, that one's messy, but we're about done with this, okay? So as I tuned it, you only got a big, nice standing mode at certain frequencies. So the next step, of course, is to calculate those certain frequencies, right? That's what we got to do next. And I forget if that clock is fast or slow. It is fast. Okay, so we'll do our 5-minute break and keep going. Okay, so what did we do? We saw some standing waves. They were beautiful. I got a little emotional. And we described them with that equation. But that equation, there's no obvious way to calculate the things that we want to calculate. The things that are important for standing waves. We've got to use that equation, but it's not quite the answer. The frequencies of those normal modes is what we want, right? Frequencies, wavelengths, right? The lambda. And nodes, the position and the number of the nodes and antinodes, they always go together. They depend on the properties of the string or of the system. And, it depends if you mean a string or any wave. Depend on the properties. So what properties are we looking at here? The length, the tension, what else have I got here? The mass of the string, the speed of the wave. All those will affect the frequencies and where the nodes are and the wavelengths. And we just got to figure it out. But there's one more thing, probably the most important thing, and how it is clamped. Okay? So if you're an advanced mathematical person, that's the boundary conditions. But here, let's just think about it physically, how it is clamped. All right, let's see. So let's go through the numbers then for the clamped string. And all that means is that at the end, the string is held in place. So when I draw a string like this, so here it is, like that. Its length is L. It's got all those other properties, mass density. It's under some tension, T. We're going to say this is the origin, and we're going to say we have deflections in the y direction, and we think about the string along the x direction. And it can move in time. Right? That's all the stuff we're doing. So all we got to do now is apply that idea that it is clamped. Okay? Here we go. What do we know? At the left end, what is happening? Way over here. It's clamped. What does that mean? That means y equals 0. It can't move up and down there. Right? It's a function that must be 0 for all time. Can it occasionally escape and move up? No, it's clamped. Right? Y equals 0 for all time. So the way we would write that in terms of this is you'd say, well, I want to know y for at x equals 0 for all time has to be equal to 0. Right? That's kind of like, that's the mathematical description of saying the left end is clamped. We don't mean everywhere is 0. We just mean x equals 0. Y is 0. So now let's just write that in the equation, see what happens. Well, let's see. We know that this 0 must be equal to a, okay, sine. What is k times 0? What is k? I don't know. It doesn't matter. K times 0 is 0. So you don't have to know what k is yet. You can get by right out there, right there. So x equals 0 makes that kx be 0. And then cosine omega t. Because it says anytime, right? So is that going to be equal to 0? Well, yeah. Because the sine of 0 is 0. So this is always 0. So what did we learn here? We learned that 0 equals 0. We learned nothing. Right. If I were reviewing that equation, I would say I learned nothing from that equation. Okay. So we're done. We learned nothing at the left end. Let's try the right end. Foreshadowing. Here we go. At the right end, what's the rule? Y equals 0 for all time. But what's the difference? X isn't 0. The difference is now we're talking about x equals L. So we would write this. Y at L for all time must equal 0. So let's see, does that teach us anything? So we plug it in, and we say, okay, then 0 must be a sine k times L cosine omega t. And we say, how could that be 0 for all time? Not just 0 every now and then. It has to always be 0. Well, there's a lot of ways. I mean, what is it mathematically? Remember, you got to be good at algebra in this class. I always worry about people's algebra. We're talking about the product of 3 numbers here, right? How many of them have to be 0 to make the product 0? 1, right? Yeah, so if any one of these is 0, we're in good shape. Okay, let's do one. How about a equals 0? Does that make it 0? Yes. Is that a good answer? No. Right? That's in physics, that's what we call the trivial solution. But here, I was just going to label it something brilliant. Oh yes, boring solution. Right? I know that the string can just sit there and not move. That's a given. We don't need to solve for that. Okay? But technically, that is a solution to the equation, is that a can be 0. So we call it trivial solution. But that's not what we're looking for, because that doesn't tell us about the normal modes. What about cosine omega t? What if we say cosine omega t equals 0? Is there a way to make that happen? No. That'll happen every now and then. Cosine goes through 0, but not always. Not always. So to make it clear, we're rejecting these. I'll put a line through them like that. Right. Not always. And let's see. But another one we could try is, what about sine KL equals 0? KL equals 0. I'll put question marks. That'll make your notes clearer later when you're reveling in this for 13 hours in a pod. Okay, how could that be 0? Well, sine is 0 when the argument is 0, so it could be true if KL is 0. So if KL is 0, then this will always be 0, and then we've made it work. Except, if you know what K is, what does this mean? K is 2 pi over lambda, so what does that mean? Lambda must be infinity. Lambda is infinity is another trivial solution. Lambda, the wavelength being infinity, means it doesn't move. Because if you calculate the frequency, then the frequency is 0. So actually, KL equals 0 is also boring. It's not one that we care about. Right? It basically just means the string doesn't move, and we know that. We know the string cannot move. We want to find something more interesting. Is there another way sine can be 0? Yes, sine of pi is 0. Ah, very tricky. Right, KL could be equal to pi. Interesting. What else is sine 0? KL could be 2 pi, or 3 pi, or 4 pi. Or you could say when KL equals m pi, where m is 1, 2, 3, 4, whatever. M equals 1, 2, 3, da, 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 da. So the positive integers, right? 0 is an integer, but it's not positive, I think. Okay. So now we've found a bunch of different solutions to the problem. And remember, what were we even doing? I forgot. We were saying, where do the nodes, the normal modes, oh yeah, we were saying, where do the standing waves happen? And we find they only happen for certain wavelengths. And then we realized, well, that's exactly what we saw in the experiment, right? When I was tuning the knob, we were getting nothing, nothing, and boom, normal mode, or standing wave. Big, beautiful standing wave. And then I'd tune it more, nothing, nothing, another standing wave. And if we had counted the number of nodes and antinodes, we'd find they change. And what you're just doing is you're going through different values of m. So when m equals 1, that's like a half of a sine going between the two things, okay? So we'll draw it more in a minute, but now let's just sort of finish it. Let's say, so, for the clamped string, let's look at what all this tells us, okay? We know that clamped string, we get standing waves when, if this is true, KL equals m pi, where m equals 1, 2, 3, 4, etc. Okay, so that's what we know. Now we want to convert that into useful physical information, because nobody likes k, right? So what we can do is say, well, we can solve it for k. We can say that the k values, the wave numbers for the normal modes, is m pi over L. That's a solution, or that's a description of the normal modes for the clamped string, m pi over L. And then we can convert that to wavelengths. So only certain lambdas, right? Because k is 2 pi over lambda. So if this is 2 pi over lambda, the pi's go away, we flip it over, we put the 2 over there, or we divide the 2 into there, and we get lambda equals 2L over m. All right? These are saying the same thing, it's just this is a more physical thing you're used to thinking about. All right? 2L over m. Let's see, we'll draw them in a minute just to see if that actually makes sense. But we also want to think about how fast it's moving up and down. So we have to get time involved, right? How fast, what's the frequency of this thing moving up and down? So you bring time in through this equation. Remember, so to bring in time, we say the velocity is the frequency times the wavelength. Remember that. Or we say omega equals vk. Those are the same thing, okay? So if we want to bring in time, then we say, well, let's solve for omega. All we got to do is multiply this thing times v. V is like a constant for the medium. V is how fast the wave moves. So we just stick a v on there, right? So omega is, I usually like to put the m by itself, and then v pi over L, right? So those are the angular frequencies of the standing waves. And then we could also go for f, right? For the frequencies, it's always just you put the v and you divide by the lambdas. So we'd say the F's are, let's see, I put you divide by the lambda, so the M is up front and the V is there, and you have the 2L there. Right. So this is most of your homework problems right here. Right? What are the frequencies and wavelengths of the normal modes? What's the frequency of the third normal mode? You put a 3 here, right? And that's how you get it. You just got to know how long the string is. Okay? Let's do an example problem right now. Let's see. Here we go. Oh, I only want one projector on. Hold on. I'm losing style points here. Screen controls. Audience right. Boom. Okay. There we go. So here's a problem you would do. This is a typical problem. I think an exact replica of this problem is on the homework. All right. So this is just saying you walk around, you see a string, and you send a pulse down it, and it comes back in a certain amount of time. You know how long the string is, right? This is in my notes. When I post the notes, this text is in there, so you don't have to. You can take a picture if you want. So you know the length, and you know you send a pulse down it. It's a clamp string. I may not have said that, right? And you send a pulse, and it goes up and back. And the question is, what is the frequency of the sixth normal mode? And draw it, right? That's a typical kind of a question. So you look and you think your formulas, and they were all, let's see, for time, you had to know the velocity. So this is one way you can get the velocity. This is just from kinematics, right? This pulse, if it goes a distance of 2L, it went around the string. That's 2 times 8.15, right? It went 16.3. And how long did it take? 0.23 seconds. So basically the problem gave you the wave speed. Okay? So that's 71 meters per second. All right, there we go, 71 meters per second. So then you say, I want the sixth normal mode. Let's see. Can you repeat why K is where? I'll do that later. Does V stand for time? Yeah, V stands for velocity. You need, to calculate things based on time, like frequency, you need the velocity. So V doesn't stand for time. V is velocity. What is V if the wave is not traveling? Oh, you have to come Thursday. Can I repeat why KL is boring? Go through the math. If KL is boring, K is 0. If K is 0, ask yourself what F is, and you'll find out. Okay. So we solved that part. So now we just go to our formulas. I mean, I don't ever want you to just go to your formulas, but in this case, you just go to your formulas. And you say the frequency is M times V over 2L. Okay? So M in this case is 6, because it said the sixth normal mode. For this kind of a system, M equals the number of the normal mode. There's an exception to that I'll tell you about later. You put 71 meters per second there, and the 2L comes down here, 8.3, right? And you get 26 hertz. And I took the demo apart. We don't have enough time to do it again, but if we set it up and did the sixth normal mode, it would be at 26 hertz. Right? So this is actually describing this exact experiment. I took a slow motion of a pulse going back and forth. I have no life, right? This is how I spend my time. And there we go. The other part of the question is, draw it. Can you draw this normal mode? So here, I guess I haven't explicitly said this, but the trick for drawing these things, the thing that's always true, is that if it's the sixth normal mode, it will have 6 antinodes. Okay, so you count the antinodes. So it's 1, 2, 3, 4, 5, 6. That sucks. Okay, 1, 2, 3, 4, 5, 6, like that. 1, 2, 3, 4, 5, 6. Okay. If you're drawing a single cycle, it up and down counts, right? Up is an antinode, down is an antinode. Up is an antinode, down is an antinode. If you're drawing this like what it really looks like because it's so fast, you then draw the opposite phase and you see big amplitude, antinode, node, antinode, node, antinode, node. But the point is 6. 1, 2, 3, 4, 5, 6. If I said how many nodes are there, one question is, do the ends count as a node? And the answer is yes. The ends count as a node. So there are 7 nodes. But the thing that will always match which mode it is the antinodes. Because we think, what does m equal 1 look like? What does the fundamental, the first one, look like? It looks like basically this. And it all kind of makes sense. If m equals 1, then lambda is 2L. The wavelength is 2L. Oh, yeah, because if I turn this into a full wavelength, it would be like that, right? And here's L. So the full wave will look like this, 2L. And if I have m equals 2, what would that look like? Then lambda would equal L. That's putting one wave in there. And if I look at it the opposite part of the cycle, m equals 2. Right? So the whole thing sticks together. Look at the plots in the book. It will definitely help. Okay? But that's that's not a super hard problem, but that's a typical problem. In these problems, it's always about how do you get the velocity. There are 3 ways I can tell you to get the velocity. One is something like this, where they tell you how fast a pulse went. 1. 2 is the system. They might tell you a string is under tension T and mass density mu. The velocity is the square root of T over mu, right, from last semester. 2. The third might be, here's an equation for the normal mode with numbers. Then the velocity is just that over that. No, that over that. Omega over k. Yeah. So often you're just getting the velocity so that you can calculate the normal modes. Right? That's a pretty typical beginning kind of a problem. All right. Let's see. So now that is really what I was going to say about strings. So now we move to sound. So let me indicate this transition. Here we go. That means we're switching to sound columns here. Oh my goodness. Why is it this baby? I can't make phones work. Oh, it's talking to my headphones. Okay. Let's see. Did I screw something up here? I don't ever mess up. Let's see. Oh, did I make something not be 16? Let's see. 2 times that is 16. Oh, this is 16.3. Just do the math. Here we go. That was my 2L down here. Sorry. Let's see. Well, what did I do there? Let me get my notes out. Let's see. F is, this is 6, right? V over 2L, 16.3. Yeah, 2 times that, 16.3. Yeah, sorry. Thank you so much. How do you know there aren't more nodes? Like, why is 7 the max? So you can get more nodes if you turn up the frequency. You can get 8. But this mode has 7 nodes because if you plot it, like if you calculate k and omega for m equals 6, and you make this graph, it will have 7 nodes. Do it. Plot it yourself. Yeah.
So, like, if you said, like, find, like, the third node or something like that,
Uh-huh.
what you were asking was, like, oh, you just, like, add one more node to it?
Yeah, if I said 7, there would just be one more bump.
Okay, so we should always, like, graph it before we draw it? Or, like, how are we supposed to know?
Oh, yeah. You'd never use that formula to graph it. I was just saying if somebody really wants to confirm this, you could put that in MATLAB. But the basic answer is, if it's the 6th mode, it has 6 antinodes. If it's the 7th mode, it has 7 antinodes. If it's the 1st mode, it has 1 antinode. Right. That's really all you got to know. Yeah. You don't have to use math to do that. Yeah. So basically, us solving these boundary conditions, you also will never do that. That's me showing you that that's true, is solving the boundary conditions. That's really all the idea. So that's all we're doing here, is we're finding the nodes, antinodes, wavelength, and frequencies of standing waves on a string. Right? And now we got to do it for sound. What are those 2 graphs on the far right? Yeah, so this is m equals 6. This is the 6th standing wave. This is m equals 1, and this is m equals 2. Right? We're just drawing the normal modes. There's lots of sample graphs in the book if you want to have a look. Is it n nodes for? Okay, so now people are asking, is the number of nodes always n plus 1? So we don't want to get too obsessed with m and n, because it'll get screwed up when we do sound. Okay, so I'll summarize all this when we're done. Probably it'll be Thursday, but you'll see. Okay, for now, the m is equal to the mode number. Okay, the 1st or 2nd or 3rd or 4th, whatever you want to call it. Okay, what is 230 milliseconds? That's how long it took the pulse to go down and back. So 0.23 seconds, 230 milliseconds. Standing sound wave. Okay, let me erase a little bit. And we'll talk a little bit, oh my God, a little bit about sound waves. What did I do? Oh, it's stuck up there again. Oh my God. Oh, Jesus. Okay. Okay. All right. Standing sound waves. Okay. We'll just get it started, and then we'll look at something that will blow your mind. Sound Okay, in an open tube. I at least want to introduce this idea so that when you're doing your 13 hours, you'll be able to understand some idea what they're talking about. Okay. So in a sound wave, every wave is a disturbance going through a medium. So for sound, it's pressure, right? So the disturbance equals the air pressure. Before we plotted y as a function, the y deflection as a function of x and t. Here we would plot the pressure P as a function of x and t. So if you're looking at a tube like this, right, like that, what the mode would look like, you could say here's L. Instead of L being the length of the string, it's the length of the tube. So that L is basically the same thing. And then we got to think about the boundary. So the string was clamped. But what's going on with the air? If we're going to be plotting pressure here, so here I'm going to plot versus x, I'm going to plot the pressure, P, and it's going to oscillate around atmospheric pressure. A sound wave is just high, above atmospheric, below atmospheric, just by like 0.1%, not by a lot. Okay? So the boundaries now are that for an open pipe, open ends are always at P equals P atmospheric. Right? So essentially it's clamped. Right? We said the string was clamped because the ends couldn't change their value. They're stuck at 0. Here, the air is clamped because the ends are stuck at atmospheric pressure. So if I now draw a molecular scale drawing here, there's some atmospheric pressure density of gas. And there's some. Right here at the end, it's the same. But what's going to happen in a normal mode is the air is going to move a little bit, and you're going to get really high density here in the middle, like this, above atmospheric pressure. And then back to atmospheric, kind of like down there. Whew. Hold on. Okay. So what that looks like is this. It's 0 here, and here at L, it's also, or not 0, it's atmospheric pressure. It'll look like that. So that's kind of like part of a normal mode. But then what do you think happens next? Oh, it's going to go like this. Yes. Like that. Oh, we have to draw it. It'll be less dots. All right. Atmospheric here, and then not so much in the middle. Right? Because it's going below atmospheric pressure there. Right? So here is the solid line. Here is the dotted line. There you go. So that's what's happening is air is kind of rushing in and out of the tube. Now really the air isn't traveling a long distance. You've got to realize it's really teeny motions of the air that change the density. Okay? So what we conclude here is that the open pipe equals the clamped string. Essentially mathematically, they are the same, right? Because they have the same boundary conditions. Everything else is the same. We don't have to solve any equations. We don't have to redrive anything. If you were okay with this, this is the same. Just change y to p. That's literally all you got to do. And make it go around p atmosphere instead of around 0. So let's write down then the normal mode stuff. And also for sound, we tend to always use frequency and wavelength. We don't use omega and k so much. So we'll just write it down in terms of frequency and wavelength and say, okay, cool. Okay, so for the open pipe, did I say pipe or tube? Let's see. Pipe. I didn't say anything. Okay, oh, I said tube there. Okay, the open tube. Okay. Then we would say then the lambda, the wavelength, equals, well, it's exactly the same, 2L over m. What is the wavelength of that wave? For m equals 1, this is m equals 1. I should just start labeling them every time. This is the fundamental. The wavelength of that is 2L. Put 1 in here, and sure enough, you get 2L. Right? What about the frequency? F is mv over 2L. Exactly the same as the string. Because it's the same, it's a different physical situation, but it's described by the same math. Right? That's what physics is all about. Let's see. La la la. Doobie doobie doo. How far along this can we get? Ooh. Ooh. Let's go for broke here, yes. 9 minutes. So I could, my notes actually say optional, so I'm opting not to draw it, because it's a lot of dotting, okay? But I could draw this for you. Oh, we need to do it, because y'all are confused about modes. Okay, so let's do the m equals 2. Let's draw the m equals 2. If that is m equals 1 in this pipe, and we do m equals 2, what's going to happen to this? It's going to get shorter, right? So let's do m equals 2. There's the pipe. Here's atmospheric pressure, right? What's it going to look like inside of there? Well, it's going to get really dense on one side. Oh my, look at that molecule, argon. Look at that. Right, and then really low over here. And what would that, if we were to plot that, what would that look like? Atmospheric, it goes up, and then it goes down, right? M equals 2. If we look at it a half cycle later, it's like that. These just switch sides, right? How many antinodes are there? 2. There you go. The number of antinodes equaled the thing. Yeah, that's okay. All right. What about m equals 3? Well, according to the equation, the wavelength's going to get even shorter. The frequencies are going up, by the way. I can't do animated drawings here to do the frequency. But m equals 3, it would look something like this. Atmospheric on the edges. It has to be atmospheric, right? And then you would get into a high density region here and a high density region here and a low density region there. Right? And if we were to plot it, what would it look like? Oh my goodness. Pressure versus x. It starts, it goes high, and then low, and then high, and then back down. And if you plot it a half cycle later, and you see the blurring, how many antinodes? 3. What is the m number? 3. It works out every time. If you wanted to calculate the frequencies, you would see that they're going up, right? So here, the frequency is v over 2L. And here, the frequency is 2v over 2L, also known as v over L. And here, the frequency is 3v over 2L. So when I was doing the string, you may have, if you couldn't tell, I was increasing the frequency to get more and more nodes to fit in there. Okay? That's what was happening. Now, let's see. A lot to digest here. Okay, so here's what's going on. Okay, so real quick, let's just blow on this. What is this? This is a tube. It's an open tube because it has a hole right there. Okay, it's got a hole right there, open. When you blow on it, you're just applying a lot of different frequencies, and the one resonant mode is getting excited. So if I were to say what is the frequency of the fundamental mode, I would say of this tube, it's F equals mv over 2L. I wouldn't use that equation. I would just write this. I'd say 1. Speed of sound in air is 343 meters per second. And 2L is twice this length, which is like a meter. We would have to measure it, right? A meter, 1. So I should get about 300 and something hertz. Does anybody here have perfect pitch? I don't either, right? If you were to measure this on the spectrometer, if I had time to put the screen up, it's about 300 something hertz. The mystery we're going to talk about next time is what happens when I do this. I want you to think about this for 13 hours. Why does it go down when I cover the end is a mystery for next time. But what I'm doing is I'm stopping 4 minutes early so you can turn these in, and so you can look at the two-dimensional version of the string wave. If you've ever seen a Childani plate before, this is your chance to play with one. I would encourage you to crank this around 300 and watch it go. I'll get you some sand. Hold on.